Okay, so hello. I will now present our work titled MaSTer, which stands for Maliciously Secure Truncation. This is a joint work with Eric, Isajan, and Bart. So I will start by giving an introduction to privacy-preserving machine learning and some background. Then I will proceed to detail the MaSTer protocol. And finally, I will finish with our benchmarking results and a slide on summary. Right, so
Oh, that's fine.
sorry?
I think both now work.
Okay, so hopefully that works. All right. So when we're talking about privacy-preserving machine learning, normally we talk about privacy-preserving inference or oblivious inference. In this case, the client has some sensitive data that he wants to get predictions on, and the server has some model that he worked very hard to train on, and he doesn't want to share it. And so these two parties can now directly engage in two-party computation. However, this is very unpractical because it imposes high communication overhead on the client, and he might not have a device on a very reliable network. Therefore, in the literature, many works consider the outsourcing case where both client and the model owner outsource their data to certain amount of parties. This is usually 3 or 4. In this work, we will consider three-party computation. Usually these works work in an offline-online paradigm where the parties first engage in an offline phase or input-independent phase, which is called also pre-processing, where they generate some correlated randomness that is used later in the online phase, which is the input-dependent phase. Now, usually, it's quite convenient to push everything to offline phase and have very fast online phase. However, in certain scenarios, this is not very desirable. For example, when you run a streaming scenario where you run an inference on some data that is streamed, you don't really have time to perform the offline phase, and the parties perform the offline phase on the fly, and therefore the offline phase counts towards the total time. That's why in this work, we'll try to minimize the pre-processing phase and minimize the total time that takes to perform the inference. So in three-party computation, the state-of-the-art is replicated secret sharing. This is a 2 out of 3 secret sharing, and the reason it's so popular is because it essentially provides malicious security for free, because every value held by an adversary is also held by one honest party. Therefore, any cheating in local computations can be easily detected by a consistency check. Now, usually, the secret sharing is performed over ring. This is to leverage the natural CPU types of 32 and 64 bits. And for this reason, we use fixed point arithmetics. Now, in fixed point arithmetics, after every multiplication, the precision is doubled. And we need to avoid overflow after many multiplications, we need to introduce a truncation protocol that cuts the last few bits and resets the precision. The truncation protocol is a nonlinear operation, and there have been many works in this domain that introduce specific truncation protocols. There are two main cases for the truncation protocol. One is probabilistic, which results in the truncated value plus or minus small error with certain probability, and faithful truncation, which results in the precise result. However, these protocols are very expensive, as you can see in this table. So here the first two rows depict the cost of the faithful truncation. They only were proposed for two parties. The state of the art in the two-party case is the secure ML truncation, which requires no communication whatsoever, only local computation, however, is probabilistic. Now, in the three-party case, ABY3 introduces a semi-honest truncation based on the secure ML truncation. So they simply take the secure ML truncation and reshare the result among three parties. That's why, as you can see, they incur a cost of one ring element sent over one round. Now, in the maliciously secure domain, again, ABY3 is the state of the art, and all of the approaches that improved on ABY3 simply improve the offline phase. And as you can see, this approach takes 3 ring elements sent in one round in online phase. And again, as I said, all of the works incur some offline phase. Now, our protocol achieves malicious security at the same cost as the ABY3 maliciously secure truncation online phase. So let's look how it works. So the main building block of our protocol is the ABY3 semi-honest truncation. Looking inside the black box, this incurs many local operations. As I mentioned, the truncation works as the secure ML truncation with resharing, and the red arrow represents the resharing, where party 1 sends one value to party 2. As I mentioned before, due to the replicated secret sharing, any cheating in the local operation is easily detected. And so to detect malicious behavior, we need to make sure that party 1 sends a correct value to party 2. To do this, we have party 2 and party 3 perform another truncation, this time 2 out of 2 truncation, two-party truncation, now in different randomness in the shares. Again, looking inside the black box, this is only incurs local operations, and then party 2 and party 3 perform a check, simply checking that the value sent by party 1 was sent correctly. Now looking inside the check, how it works. So know that party 2 and party 3 hold 2 different secret sharings of the same value, one from the ABY3 truncation and one from the secure ML truncation. Naturally, to check that one of them is correct, they could compute the difference and check whether the difference is equal to 0. However, in this case, it's not so easy because both of these truncations are probabilistic, and therefore the parties need to check for an interval whether the difference is in -1, 0, or 1. Now, because we are checking for an interval, one might wonder what happens when malicious adversary now tries to cheat. Can he now introduce certain error? So looking more closely to it, malicious adversary can send a value with some additive error, which would result in the shares of ABY3 with additive error, which would then show in the check. Looking more closely to the check, the truncation of ABY3 reconstructs to the truncated value plus this small error, as I mentioned. Same for the secure ML truncation. Now, when we cancel the truncated value, we end up with this equation from which we can derive that any adversary can add now small delta, which can be less than or equal to 2. However, this is highly probabilistic because the adversary can only add delta equal to 2 when E minus E prime is equal to -1. As it turns out, the probability for this is very low, and therefore in our work we only consider the case where adversary can add plus or -1. So this is equivalent to influencing the least significant bit. And in fixed point arithmetics, this represents the value of 2 to the minus d, where the d is the set precision. In our paper, we have explored this behavior, and in our network that we run, we made the conclusion that with higher precision, the adversary has a lower influence on the network. Now notice that the output of the protocol is the output of the ABY3 semi-honest truncation, which is completely independent of the check, and therefore we can push all the operations in the check to a post-processing phase, saving us some rounds in the online phase. Now, looking at a bigger picture, we benchmark our protocol comparing to ABY3 truncation. We run an inference of a 5-layer dense neural network with ReLU and softmax activation functions. And we implement this in MP speeds, and we simply replace the truncation protocol by ours and the ABY3 one. Now, simply by replacing this truncation protocol, we we improved the throughput by a factor of 2, the total throughput of the inference. To conclude, our protocol is a combination of 2 semi-honest truncation protocols, where one semi-honest truncation protocol is used for the output of the truncation, and the other is used to check the correctness or check for malicious behavior in the first one. We can also push this check to a post-processing phase, saving us some rounds, as can be seen in this table. So our online phase consists only of 1 ring element sent, and the post-processing is the check where the value is opened. Now, comparing this to the ABY3, which has the same communication size in the online phase, however, their offline phase is very heavy. Our work also introduces a new adversary model. This is because we check for this interval, and this allows the adversary to add or modify the intermediary result during the computation. And even though we explored this behavior in our work for this particular network, it might be interesting to explore this in future works as well. So, thank you. Any questions?